Okay? And one of the surprises was this reaction here with benzaldehyde. So benzaldehyde somehow not only gave the monoacylated product and quite a nice yield, but it also gave this bisacylated product shown here. The compound itself is very interesting from its structure because these carbonyl groups here cannot be planar anymore with the aromatic rings. And the two phenyl rings here that come in with benzaldehyde also have to avoid each other and form a kind of a sandwich. We puzzled for a while about the mechanism of this acylation. We tested a few hypotheses, and finally we noted that when we irradiate the clean, purified, monoacylated compounds under the reaction conditions, we somehow magically got this bisacylated product. We have no idea about the mechanism because it formally involves the loss of a hydrogen molecule, and that is rather unlikely here. We then went to reactor optimization, although we did that much later. The problem with the procedure was it required 5 days of irradiation, and nobody has really 5 days of time. The yields were not so bad. The problem here is that the product you're forming is a much better chromophore than the compound you're starting with. So when you have higher conversions in this reaction, your product starts to steal the energy of the light. It doesn't do anything with it. It may form the bisacylation product from it, but it typically undergoes a keto-enol tautomerization, and when the light is turned off, it goes back to its ground state. So we started a bit of an optimization study. We went away from the conventional setup, which is the immersion well type, and we moved towards these black boxes. The black boxes have the advantage you can put in different lamps, and the lamps have a much nicer, a more narrow spectrum of the wavelengths that you're getting. And we tested here a range of different light sources and wavelengths and also direct sunlight. And we looked at the radiation time and we looked at the isolated yields. And we noted that when we used 300 nanometer light in this black box, we got the best chemical yield with the shortest reaction time. And of course, and that is something where I have to blame myself, we should have known much earlier. Because you need to know your science, you need to know your equipment. So basically what we did is we recorded 2 UV spectra, one for product, one for the starting material, and we looked basically at a region where the starting material absorbed better than the product. And then we picked the proper light source that definitely or that actually covers exactly that area. And the 300 nanometer light source did that very nicely. So the blue line here is the important line. And the light source pretty much tickles now the starting material over the product, and you get faster reactions here. The yields were also not only higher, also the purification was very simple. Evaporation followed by washing with hexane. That's all you needed to do. And it's a very simple procedure. We went then on and discovered a few more things. So for example, with this di-substituted molecule here, we get monosubstitution. We thought for a while that this is the correct structure. It was not the first time that somebody had done this reaction. It had been reported already in the literature. The NMR, of course, didn't tell us anything, but we were able to grow a crystal and got a crystal structure. And we noted that down here, one of these acetate groups had rearranged. So there was a 1,5 acyl shift happening down here. We don't know if it's thermally or photochemically stimulated or ignited. We only know that's obviously occurring, and that some of the literature data obviously had ignored that. Yields were quite nice. This was our target compound at that time. It's a very interesting naturally occurring quinone. It has magical properties, very highly bioactive, and this was just a simple analog towards this. What we noticed is we have up here a number of hydrogen bonding happening, in particular the one of the hydroxy group to the incoming aldehyde carbonyl group. And there's no rearrangement happening up here, so we believe that down here, obviously, there is hydrogen bonding happening between the two sides, and that may actually start the whole rearrangement process. All right? Whereas up here, this hydroxy group is protected in the hydrogen bond that it forms to the wrong direction. We studied the regioselectivity of this compound by just adding one substituent here in the 5 position, and we got both regioisomers. We got some crystal structures for some of them, and here are just 4 examples that I investigated during my PhD, and you can see the yields are okay, at least the overall yield. Sometimes we get bis addition, sometimes we don't get any. And the 2,8 isomer for aliphatic aldehydes always was the major one, and that was good, because that was the regioisomer that we desired, because our target molecules at that time were these pyranonaphthroquinones, and they required exactly the regioselectivity that we found. The only exception was the benzaldehyde case again. Here the 2,5 isomer was the main one, but however we believe that maybe selectively the 2,8 isomer is here converted to the bis acylation product, although we haven't really proved for that, because I have left the group of Professor Mattei then and moved on somewhere else. We were able, however, to control the regioselectivity entirely by adding lithium perchloride. And the lithium coordinates now towards these 2 oxygens, and you get now regioselectively addition to the carbon 2 position. Unfortunately, it's the wrong regioisomer for us. But at least it allows you now to make structural analogs of the naturally occurring pyranonaphthroquinones, where you have this hydroxy group on the other side. So it may not be so bad. We did a bit more than that. This was already done by my successor. So we put also substituents at the double bond of the quinone. And now the products were very unstable. They were very sensitive towards oxidation just by air when you did the workup. And that was good, because ultimately we were interested in these quinones anyway. So here we got, although not in great yields, we got these compounds. In one case we isolated the intermediate. This was our target at this time, another class of bioactive quinones. Some of them had antibiotic properties, so that was quite interesting. And you always want to demonstrate to industry that your chemistry is relevant. And for the pharmaceutical industry, of course, the relevance lies in I can make bioactive compounds with my method. All right, we also tried then 2-methyl 1,4-naphthoquinones, and here we isolated this very unusual triketone. So it occurred from addition to, well, the other carbon where the methyl group is. And you're not getting a naphthoquinone back here, you're getting a triketone. Published that in Tetrahedron Letters a number of years ago. And then finally, we thought, well, this is all done in benzene or acetonitrile. And benzene and acetonitrile are very good solvents for the chemistry, but they are also highly toxic. So we teamed up with some people in Belfast, and we investigated ionic liquids as an alternative. For a number of years, there was a big hype in ionic liquids as the green solvents. I can tell you that making ionic liquids is not very green at all, and it's also quite challenging to work with them. Anyway, what we did is first we screened a number of ionic liquids. We looked at the conversion, so this is the leftover naphthoquinone. We looked at the amount of product formed, and we looked also at the reduction product that is formed here as well. And we found that these 2 ionic liquids here gave the highest selectivities. So we focused on them, and we studied now a range of different aldehydes, and they are all shown here. The problem here is isolation. So these numbers here in brackets are actually isolated yields. It is very difficult to isolate a very polar product from a very polar reaction mixture as ionic liquids. And here the yield, actually, the selectivity looks nice, but the yield is only 10%. The rest is trapped in the ionic liquid, and you can extract as often as you want to, you're not getting it out. So we found that ionic liquids are probably a bit overrated. They can be used, but they have also their limitations. And then finally, we went into production, and we used one of these reactions, and I showed it when I was here last time already. We had a different focus, and we did this reaction outdoor on a 0.5 kilogram scale using this solar reactor that is installed in Germany, in Cologne, at the German Aerospace Center. half a kilogram of quinone. That's quite a difference between 500 milligrams that we used in the laboratory. 5 liters of aldehyde, and after 3 days we had a yield or conversion of 90%. So this reaction was extremely productive. When we analyzed the data for the weather, however, we noted that only the first day contributed to most of this conversion or chemical yield. Because only on the first day we actually had pure, beautiful sunshine like right now outside. The other 2 days were very overcast, so basically there was very little chemistry happening in the other 2 days. And that is supported also by the weather data, and with the help of some equipment you can calculate the amounts of photons that you collect. And of the 300 moles of photons that we collected with the help of this reactor, more than 250 were actually collected on the first day only. We expanded that a little bit a few years later with a different reaction. And here we were interested in comparing various types of solar reactors. Not everybody can afford such a highly sophisticated thing like this one, which is known as a Profis. It's only one existing in the world anyway. But these are other reactors that are much more simple, but they have their advantages because these two here can also use diffuse light. And that is the light that you have when it's cloudy outside. All right? We set then the same reaction parameters for all these reactions. So here it was 58 liters of solvent, half a kilogram of aldehyde, which is a solid this time, and 175 grams of benzaldehyde. Now, this reaction, unfortunately, was a bit of a disaster, but the reason for that was simply we had a very bad experimental time. When you collaborate with a research institute like this, they give you a time slot and you have to go there and you have to do the reaction no matter what, no matter if the sun is shining or not. And you can see that here from the picture, we actually ended up with a very bad weather period. And when we analyzed our reactions here, we had a conversion of 40% of this was gone, but of the product, we only had 7%. And this reactor here ultimately performed the best because of the 53% that were converted, some 17% were actually product. So here we had a lot of byproducts, we had a lot of side reactions, very unfortunately. And this reactor here is static. There is just, you fill the reactor, you leave it outside. And because of the cold night, the tetrabutanol froze that we used as a solvent. And there is no solid state reaction happening here, so we needed a lot of time in the next day to dissolve it all again. And so this one performed actually the worst. And of the 3 reactions, I only want to show you this one more time. This reactor is known as a CPC reactor. It has a very interesting design of the mirrors. So there is a round W mirror behind this. And in front of it sits the glass tube, so your reactor. And the tube is actually as wide as the whole mirror. So this cartoon here doesn't represent really the reality. But this cartoon shows you that from whatever angle the light comes in, it gets reflected onto the glass tube. And that's exactly what you have when you have diffuse light. The light comes in from any angle, and you're still able to focus it onto your reactor. The pink line that you see here is the radiation profile. It looks like an IR or a Raman spectrum, but it's actually the amount of radiation that we had on that day. If you have a sunny day, you get like an arch-shaped curve. We get an IR-type curve, and that tells us simply that we had very bad radiation conditions. And that explains to some degree why the reactions were not so great. You see that the starting material nicely disappears and the product is actually formed, and the product also corresponds to the amount of light that you offer. Okay, it corresponds to some degree here. Again, we were able to, we correlated that with the weather data, and this reactor is less powerful than the other one, but it performs under typical German conditions that are cloudy as well as sunny, the best. So low tech is sometimes better than high tech. That's the message here.